all decimals terminate. They don't all stop. And one of the very popular ones that you've seen again in your life is the number 0.3 repeating. Right? What's that fraction? 1/3. So what this section is going to be talking about is decimals that have that kind of property. They're non-terminating decimals. And for what we're working with, our non-terminating decimals that we're going to be considering in this section are going to be repeating kind of decimals. So do you remember when it was that we said, we talked about this already today, when it was that we said that a decimal is going to terminate if we take it from fraction form and turn it into a decimal? Good. Okay, so this happened if the reduced or simplified form of the fraction let's not say is, let's say has a denominator with only factors up to, let's say, and or 5. And of course, as we mentioned earlier with the end, that they have factor, we will have factor 1 as well, but we know the prime factors. Okay. All right, so the issue then is, what if a fraction can't be written that way? So if you have a fraction that can be written as an integer over an integer, then the non-terminating, that word non-terminating means repeating. And that's what we're talking about in this section. So we're not talking about irrational numbers. We're not talking about square root of 3. We're not talking about pi. We're talking about things like square roots, we're talking about things like 1/3. Okay? So we're talking about non-terminating decimals that are repeating. So here's an example. We've got the number 1/24. And let's first of all verify as we look at it that in fact it is a non-terminating decimal. And the way that we do that is we factor. So I'm going to do the same factor diagram that I did before. Though of course you don't have to. What's the smallest number that goes into 24? 2. Smallest number besides 1. 2, and if I divide I get 12. Smallest number that goes into 12. 2 again, and I divide I get 6. Smallest number goes into 6. 2, I divide and I get 3, and I'm done, because those are all prime. Now I've got 3 2's and 1 3, and it's not a terminating decimal because it has a 3, right? And 1/24 is already reduced at the top of the line, right? So that 3 tells me this is not terminating. But it doesn't mean I don't have a decimal representation. So how do we find the decimal representation? Well, we find it the same way. It's just that it usually ends up being messier. Yay, right? So let's take a look. So we still take the 24 and we put it on the outside. We put the 1 underneath. And then we put the decimal point in for what would come after the 1, and we put in some zeros, because we probably need several. So 24 doesn't go into 1, and it doesn't go into 10, but it does go into 100, right? How many times will number 24 go into 100? 4, right? It'll go in 4 times. So I make sure that I put the 4 on top of where the 100 is that I'm looking at. I ignore the decimal point. I'm just looking at the 100. So it goes in 4 times, and I multiply. What's 4 times 24? It is 96. And I subtract. What's 100 minus 96? 40. 4, and then I put the 0 down. Sorry, 4. Yeah, not 40. 4. All right, so now I pull the 0 down. I've got the number 40. And we look for how many times does 24 go in 40? Just once, right? Just once. And then I write a 24. All right, so what's 40 minus 24? It is 16. And I put another 0 up here, and I bring it down, and I've got number 160. How many times will 24 go in 160? And what is 160 minus 144? 16, which should sound familiar. You already got a remainder of 16 once, didn't you? So if you repeat this problem, you know, if you keep going from here, you're going to do the 0 down. You're going to have 160, it's going to go in 6 more times. And you're going to multiply it 144. It's going to keep that pattern going. So it's at this location I know I can stop because the remainders repeated. And it repeated immediately, like in successive steps, right? So it's always going to go in 6 times from that one. What that means then is that it is only the 6 that is repeating up here. Now, I need to go back up to my original problem because I didn't really write everything out properly. My decimal point needs to come up from here, and the 0 needs to come up because it did not go in any times in the number 10. So this decimal representation is actually decimal point 0416, and only the 6 has a bar on it. Do not make me guess where that bar is supposed to be starting and stopping. Be very clear when you're doing it, okay? We call this kind of decimal a repeating decimal. And we call this repeating block, in this case it's just a 6, the repeat end. I'm not sure I spelled that right. I think it's spelled differently. Can I add at the bottom? I know your calculator can do this, and I'm happy till the day is long when you check with your calculator, make sure you did it right. I expect to see that you write out long division. Okay, that shows me that you know what's going on when the problem's going on. All right, so find a decimal representation for 29 divided by 99. So we're going to actually do the same problem that we just did a minute ago, and we're going to do the division. And I think this is the last one to start stuff with today, because then example 3 actually goes the other direction, turning it into a decimal back into a fraction. So if I take a look at this one, I'm supposed to find a decimal representation. I always do that the same way. I put a 99, the divisor on the outside, the denominator, and then the numerator is the dividend, it goes underneath. And obviously 99 does not go into 29, so that's 0. So I need a decimal point with a 0, but 99 will go into 219. How many times? Almost 3. But not twice. Yeah, twice, not quite 3. 2 times. What is 2 times 99? What's 2 times 100? 200, right? So we just take 2 off. 198. So what's 290 minus 198? 92. Okay, so then I put a 0 on the end of this, and I bring my 0 down. How many times will 99 go into 920? Let's try 9. What is 9 times 99? I think it's 810 actually, isn't it? No, yeah. I'm sorry, I misunderstood. That's good. Yeah, 9 times 99 would be 80. 810. That doesn't sound quite right. 890. Here we go. I wrote it wrong anyway. 890. And what happens if I subtract 920 minus 890? It's not 890. It's 891. Okay. I should be getting 29. Do I get 29? Yeah? Do I get 29? And I want to say that I'm done. How do I know that I'm done with 29 at that point? So which 29 does it matter? Does it matter that it's the 29 here, or that it's the 29 from here? It's the second one, right? This was the original remainder, quote unquote, right? And I now have my remainder matching right there. So if I were to repeat this process again, 29, it would go in 2 times. And then I would do it again, it would go in 9 times. So the portion of this that's repeating is both the 2 and the 9, not just the 9. That's how the last one was, right? because the remainders occurred in the exact same successive step. So this isn't 29, right? Their step before did not have a remainder of 29. It had a remainder of 92. So this actually came back to the very beginning. So everything from their beginning on was what was repeating, which is the 2 and the 9. So my repeating decimal is 0.29, and the 2 and the 9 would be repeating. So the next time we pick up in this lesson, we will learn how to go the other direction with our conversion.